All right. Hello, hello. Welcome back. All right. Let's do some research. So last time we had a little bit of issue with kind of like variables and sharing them between threads and scopes and stuff. So I'm gonna do a little bit of research here to see how just a small C example is doing it. Now here, for example, we have, okay, let's do this. Let's do yeah, just this part is enough to see that, okay, well, we have an argument. Where is this argument? So basically here's a stack frame, so it's saving the previous stack frame here, and then we set the stack frame to the current stack pointer. So this is the new stack frame, and then we're setting stack frame -4, which is like so the current stack frame. So the current stack frame pointer. So that should point to the next thing on the stack, right? Or is it pointing to the current? I don't remember. But we take -4, basically saying that we're putting it at that address, and that's EDI, which is something we get from outside when calling this function. And then at the end we're popping as well, because we do one push, so we pop. Okay, and then let's say we have an I here. That doesn't do anything, but let's say that it's 0. Okay, so now you can see we've got another thing here. It's an int, so apparently that's 16 of these, 16 bytes, which is initialized to 0. Okay, so that's like put at the same point, and then we'll do like a for loop. Okay, and here we can see we have J. It's too bad we can't see like which variable this is coming from, but we can kind of see if we hover over here. We see that, okay, well, I is over there and J is over there. So you can see also now that down here we're referencing, you know, stack frame -4, and that is like just as we're doing in our thing where we say stack frame plus something. This is the equivalent, except this is like in a real computer, or yeah, not in that virtual machine. This is on native. So this, yeah, x86-64 processor, and so the stack you have to do minus. It goes like down or up or whatever. So this means from the stack frame, and then 4 spaces into our stack, we're putting we're adding, well, that is the this same pointer here basically. So J is also put, as you can see, J is put together with everything else up here. So that's like, it's kind of like gathering all these, putting it at the top. However, let's just test something here. Let's just say that, hey, if J is 0, then we'll make another thing called x and set it to 5 plus I or num or something. And then we will set I plus equals to x. Something like that. Just to have something in there. So now we can see that, okay, here we have kind of like another thing. We have RBP minus 12 as well. But this still says 20. I'm not sure if that is because of some alignment. Hello, Rukituki. Welcome back. What's going on here? So I'm kind of doing some research on how basically like local variables are shared between different scopes. Now, of course, in here is like everything is on the stack, so it but also like, let's say you have a bunch of things in here, like, so basically how this works, right? I'm not sure how familiar you are with C and the compilation here and assembly, but basically here's a function, right? And so how we call this function is well, in assembly we basically jump in here and start executing these instructions, right? And the question is like, where are the local variables stored? And the answer is they are stored on the stack. And so you can see here, for example, num, of course, it's an argument, so it does come from outside. But in the local context, it's also stored on the stack. But it comes in as you can see there on the third line here, it comes in from the EDI register, but it's stored in this place on the stack here. Okay. And I have I, which is stored on the stack at this place, like stack frame minus 4. Now what's interesting here then is that the stack frame here is like runtime known only. However, these addresses like minus 20, minus 4, they are comp time known, like the relative kind of address of these, which is very important because that's how you can know which one you are kind of referring to at these different points here. So what I tried to do here is try to see, okay, well, what if we add another local variable in here, and how does that affect the thing? So here we say that, okay, well, x is equal to 5 plus num, and so that corresponds to, so we're using ex, which is like a general purpose, you know, register to store num. So ex is like taking the role of num here, or we're having it in the register, and then we add 5. I'm not sure if we need to do that, if that is, or if we could just add 5 directly to this. I mean, this might be like a compilation. You know, we're doing it the easy way first, and then we optimize later, probably. Okay, so then we have num plus 5, and then we need to store it in x, and x is here, so x is minus 12 from the stack frame minus 12. So that is now, nothing changed up here, but my guess is that why it jumped to minus 20 here is because of maybe alignment. I'm not sure, but that feels like one reason why you could do that. Now what happens then if we introduce yet another variable and set it to 10 plus num? Okay, so this still is the same. I see, maybe it's because it looks like this is only 4 bytes long. Like x is only 4 bytes, which doesn't make sense. Is it 4 bytes or is it... Not sure. I think these are bytes. Because this starts at 12 and then this comes in at 16. So that's just 4 bytes, right? And then this is another 4 bytes. This is 4 bytes, 4 bytes. So these are 4 bytes. Yeah, okay, that makes sense. They are 32-bit. Yes, yes. 4 bytes is 32-bit. Because you have to take 4 times 8. If it was 8 bytes, it was a 64-bit number. So these are 32-bit numbers. Okay. Yeah, I don't think there are any optimizations right now. But we can try. I don't think there is any. But okay. Let's now introduce yet another one, because now we're pushing up against this -20 here. So something should happen up here. Or, yeah, we'll see. So let's do Z. Oops. It actually compiled there. It's weird. Yeah. See, now it pushed to 36, even though we just need 4 more. So it could have pushed to 24, but it actually added like 16 here. Okay, but it basically means that whatever's happening up here is affected by what's happening down here. So, hello Zen, what's up? Welcome back. And yo Dialog. Yeah, so maybe it's not enough to just have I mean, we can still, like, we could treat these as labels that will get filled in later depending on the context. Because right now I'm doing the same thing here, except I don't modify these things up here. So yeah, so we could treat this as kind of like an unknown labeled address. I shouldn't use label because it's technically not one of these labels, but it's basically an unknown address right now, an unknown like relative stack address. And then it's just, I mean, it's just a matter then of assigning each thing to their own place in the stack. Yo Penguin, what's up? Yeah, you mean why it bumped up to 36 from 20, even though we only needed 4? I think it's alignment, but I don't know. Like, it's... I guess we could... Which one is this? GCC 15.2? I get... Oh, 1 second here. Alright, I'm just gonna go get the door here. BRB. Alright, sorry, I'm back. Just got the food at the door. They usually say they're here when they are not, and that was the case today as well, although they were farther away this time because it took a little bit before they came here. Okay. Let's see. Okay, similar output, same alignment, right? So we got I'm right, J number. Yeah, but this is more like this. This is like ordered a little bit differently. 8. But no, this doesn't have the same alignment actually, because the other one went up to 36. This just uses like the stack like packed here. If you compare to, I mean, it doesn't really matter that much, but here is like it goes up to 36. We've got some space between, like some padding. But yeah, it doesn't really matter. I think maybe I like Clang more, maybe. And then what else do we have? BPF, GCC. I don't know what that is. Oh, different architectures, right? 64 or 6502. No, doesn't work. Okay. This is like longer output. But okay. And also kind of looks like a different language here. Not sure. But yeah, same principle, everything here. Okay. Yeah, so I think that's what we need to do maybe. We need to kind of, well, but this is not really the problem that we have right now. It's like because the problem that we have is that, let's say we have like we need to transfer into like another thread. That's the problem we have. So let me show the thing here. So here's the thing. Well, in our language, the blocks are not only different scopes, but they are also different threads as well. Hello, Lord Kota. What's up? And so when we refer to something here, in here, that means we're also transferring to another thread, and that means we can't have it on the stack. Or I mean, we can have it on the stack, but we need to transfer it somehow to the other thread, because each thread have their own stack. So that's the problem we're trying to solve. Now, this was kind of a solution, perhaps, to see that, okay, well, we're requesting X, so let's put it on the heap, because that's shared memory. And then let's add that add a pointer to the heap where we keep the value when we create this new thread. So this new thread will have access to that shared memory pointer, and it would have access to the value. And then we would use like a special register to refer to X here. We're using like TM, which stands for transfer, or transfer memory, or yeah, something like that. And then plus 0, and then this would be like this would be the pointer to X, basically, to the shared memory of X. So that was one idea. Another idea is to simply make fork into a variadic instruction that will take any number of push arguments here. So this, it gets pushed on the stack. Presumably this would maybe also get pushed on a stack, and that we don't actually need a register, maybe. I don't know. And then, but instead of pushing these on the stack, we would push whatever things we need, like X, we push X on the stack again, so we kind of copy. But the problem then is that what if we have like world. I'm gonna do this because let's say S is put on the heap. S is on the heap. Actually, yeah, it is put on the heap. And this is the, okay. No. But essentially, anything that's put in here is not going to be on the stack, basically. Lord Kutte, I spoke to you a few months ago about building my own app. How's it going with the project? I don't remember. What kind of app was it? But yeah, with my project, yeah, it's going good. It's a lot of fun trying to figure it out. But I'm currently right now trying to crack like a pretty hard problem for me. So yeah, so the idea is that we can push any number of things onto the new thread, and then we'll use that for the pointers in here. So it's kind of like calling a function with stack-based arguments, sort of, except we're transitioning into a new thread which has its own stack as well. But yeah, so essentially it means like referring to X here essentially means that this thread now needs X as an argument. So we're essentially turning this into kind of like a function that takes X as an argument, and then this also needs to be, then we need to forward X as well through this thread, because the block itself is another thread, this is another thread. So X needs to be like, it's requested here. It means that this thing should, so we could do something like some kind of context where you can request things from outside, from outer scopes, and it would kind of mark this as requesting X. And that would get wired up, and then yeah, that could be something. I changed my name, used to be James Cotter. Okay. I think I asked how hard easy it would be to learn coding and do it myself. I ended up deciding on using Flutterflow. But good to hear that you're making progress. Okay. Were you the one who used a bunch of AI tools? I don't remember exactly, but no, it wasn't you and me who talked about AI tools like in a private call. Yeah, so this is still kind of gnarly here. Yeah, we could go the context way, or we could somehow, if we could somehow get to X without having to do that, that would be probably the simplest and best solution in that case. But I don't see a way right now of doing that. Because it's also like, okay, well, yeah, you could put it in a heap in like a shared memory space, but then, okay, but then how do we know? How do we get to the shared memory space from here? That is the next issue. And this was kind of the solution here, to have a register or push it on the stack, basically. We don't really need another register. We could just push it on like a pointer here that points to shared space, to shared memory. And then we need a new kind of location here that talks about, okay, well, it's the shared memory pointer plus some address, relative address there, and that would point to the correct thing. So that could solve that issue. And then actually we don't really need, well, okay, we still need this to transfer it over here then, though. That's also an issue, I think. Was a product designer. Okay. I haven't had a product call. It must be someone else. Yeah, okay. A person of your current live code is something I want to release publicly. Yeah, I get that. I wouldn't either, to be honest. Like if I can't look at the code and verify what's happening, I wouldn't feel comfortable with it either. I mean, sure, you could do extensive testing as well, but you would have to do it very systematically and try to see what's happening at every step to make sure nothing weird is going on. Okay, well, let's say we do this. Let's say we push the pointer here. X refers to this now, plus something. I mean, technically we don't really need to have a special value for that. That's just a stack pointer, relative stack pointer, that points to this. Although then it needs to be also dereferenced as well, like twice, I think. Well, I think the problem is maybe also that when you create a thread in C, what actually happens, or like in the operating system, in Linux, for example, like you can call fork, which kind of, it spawns a new thread at the same place. Does it copy like all the things, like the stack and everything? I don't actually know. All right, Penguin. Zen, can you explain me why we're building a compiler for an interpreter language? Yes, I do. Okay, so, well, it's okay. As I said yesterday, like it's not compiling to an executable. It's compiling to a new language. So basically building two languages, you can say. So the first language is what you see here. This is like the kind of more language that you would be coding in when you're coding in Runic. And then this language over here is also part of it, but this is the IR language, or the intermediate representation language. which is then interpreted. So we're not interpreting this language and running this language directly. We're interpreting this language here. Users will just code in this language. So they wouldn't even need to do anything with this. This is just a way for us to translate the program into a more into a format that we can execute more easily, I guess. Well, I say easily, but execute that we can execute, and having things like virtual threads, streaming pipes more easily and stuff like that. The plan is not to build like a compiler to native code. That is not the plan. Like, the plan is to stop here, like yeah. Excuse me, but when you have a binary like rn, myscript rn, what will happen when you launch that? Yeah, so the way you would use it is that, just like in Bash, you would either you would use runic, the runic executable, and now we have to add this flag here if you want to use IR, but basically you would use runic. Let me show this one, for example. Well, we don't need enable IR for this, but basically you would just run runic IR basic .rn to run IR basic.rn. So it just like Bash, and this one could even be run by Bash because it has the same syntax right now. And also, just like Bash files or sh files, you can do this, for example. Or how is it that you do like n and runic or something like that? I don't remember. And then you can do mod plus x, and now we can run this directly here. So so it's kind of, you can use it just like Bash files or .sh files basically, except you're using runic instead of Bash. Right. Just grabbing a slice here. So I hope that answered your question there. If you have any more questions, feel free to ask. I was actually contemplating on doing something else this stream, but then I just wanted to make some progress on this. Started to look at the compiler explorer. I think maybe this is kind of like an issue that we don't really, that maybe doesn't exist in other languages. We'll see. I mean, of course it does. Like, I was gonna see, okay, well, fork in, I would assume that fork just creates like a copy of the current execution context and then continues with that, maybe. Except the thing that changes could, like, you could get like process ID, you check if it's the child or whatever, the parent. But in this, it's like, we don't copy any, we don't get like the previous stack. Maybe that's what we could do actually. We could actually, but then the problem still is like now we're in a different stack frame. So that wouldn't work. So if you have already executable script with basic instruction echo, why users will compile to generate IR? Just need to answer. No, I mean, no, the generation of the IR happens internally in the Runic executable. The user wouldn't need to know any of that. They would just, they would just write the IR, or not the IR, sorry, they would just write the normal, Runic file, just like a bash file, and then just run that. Like the IR is only for internal it's just how the Runic file is ran when you run it. So the users wouldn't even know that is happening. Unless you want to debug it, which you can, then you would see the whole machinery underneath. But not when you just run the Runic file. You wouldn't need to know the other language for that. But you're trying to generate something like assembly. It's a language feature that you could generate binary of Runic scripts. No, that's what I'm saying. The goal is not to compile to native machine code and generate binaries. I mean, technically, we could do something like a bytecode thing. Like, we could make a feature that would compile the Runic files into a bytecode format that then would be interpreted and ran directly without having to be compiled first. But I would like the compilation I would like the compilation to be so fast that we don't really need to do that. Because the point of the language is not to be speedy. The point of the language is just to be easily written to solve some, random issues that you want to solve. Like, it's not going to be, a generic programming language that you're going to use for real programs, so to speak. It's like it's more used for like, quick and dirty scripts that you just want to fix to solve some problem. Like, I mean, it's the same. It has the same use as bash scripts. And I know that, of course, in bash you can write potentially any sort of program, but it's like, why would you if you wanna write like a program that needs to be performant, you wouldn't use Runic or bash. You would use something else. PHP, you're building something like Zend engine. Oh man. Well, yeah, I know PHP, but and I do think I remember something about Zend engine, but I actually don't really know what it is. Zend engine. Open source scripting engine, core runtime environment for PHP. Compiling PHP source code into intermediate opcodes, executing. Okay, well that sounds, what like Runic, like compiling the code to intermediate code and then interpreting that. Yeah, that sounds very similar, yes. But it's not like you're gonna get a bunch of files that has the intermediate representation in them. It's just that internally, when you run Runic, when you run this, you run this file, what's happening behind, like when you run this file, you just run it, right? But what's happening under the hood is that it's compiling this, it's converting this to bytecode or opcodes, or you know, some kind of assembly-like language, and then we're executing that language. Yeah, no problem. Yeah. It's just because of it's just to solve issues regarding how some internal mechanisms work, especially around the pipelines. When you want to build, you know, pipelines like this, and you also want to have, for example, you want to have some kind of block. Well, let's actually have it. Let's say, well, let me open up another file. Actually, let me open up the block file. You want to have some kind of block thing like this, or a function call, and then pipe that into something like grep or something else. What this is like, what we need to have here is, for one, we need streaming pipes, because we don't want to have to wait for this block to complete before we go to the next step. We're streaming whatever this block is outputting, we're streaming into grep so that we get the output directly, right? And the bash does this, and we want to kind of mimic that. So basically what it means is that this block goes here, executes echo something, but then it needs to kind of wait for echo to finish before we go to the next one. But it also needs to stream this out here. So we have like multiple executions happening at the same time, and that I've solved with virtual threads in the IR language and the runtime, the virtual machine kind of runtime that goes with it. So what's happening here is basically that this is being spawned in its own thread, or a virtual thread. It's not a real like OS thread. It's a virtual thread in our virtual machine, like the Runic virtual machine. So this block has its own like kind of virtual thread, and then this has its own virtual thread, right? And in order for us to actually be able to do that, I wanted to have a language where you get just a list of instructions that you could step through with context that you can kind of like, you know, registers, stack, the memory, the heap memory, now all that context with you, so that basically you have these snapshots of the execution, and then you can just continue execution later. Because we want to call this and then wait for that. At the same time, stream this out, which is another execution happening at the same time. So that's another thread, right? So that's why I was thinking like, okay, well, let's make an intermediate language so that we can turn this into a list of instructions that we can then, you know, step through and create virtual threads and all that. So that is the reason why we have the IR at all. Like at first, I actually interpreted the AST directly, but quickly ran into issues when we tried to do something like this. This was like a hard problem to solve when we execute. Like, it's not impossible, but it required a lot of stuff in order to kind of fix this, to be able to run this with just evaluating the AST directly. And we needed to solve the kind of same problem, like being able to kind of suspend execution and then continue it later. And then IR was just like a natural step for that, because that solved all those issues. Although now new issues arise as well. So with the bindings here. So we have more issues to solve. But I think we're on the right track because it has like a lot of potential. I know that this is solvable. I just need to figure out what to do here. Sorry, just taking a slice of pizza here. Alright, thanks. See you later. Unfortunately, we're kind of stuck here. It's kind of like, hello, Kai41K. What's up? Welcome. We're kind of stuck here because this requires some thinking here. Well, what if we did copy the context when forking, so that we like inherit all the stack, and then it's just like we continue, because how this works is like the fork is not really like a fork in like C or whatever or Linux. It's like we're forking. What that means is that we have this here, which is the destination of the fork. So basically this means it's gonna jump to this place where it's over here. So the thread that we're spawning will actually spawn in a separate place. And then the kind of context of the thread is being passed here. Whereas this is kind of like, you know, the first one is like the first item on the stack, second item on the stack, third item on the stack. But then we lose everything else. Like on the stack, we lose that context. So maybe that's what we need. We don't spawn an entirely new thing. We have to kind of copy the stack. Maybe. Linux kernel implements copy on write when fork is called. When syscall is executed, the pages that the parent and child... Oh, that's on the heap. But it copies the heap? Hang on. So the question is, copy entire process heap, and then there's some answer here. The pages that the parent and child share are marked read-only. If a write is performed, a read-only page is copied as the memory is no longer identical between the two processes. Oh, so it's actually not shared, it's like copied over and then synced. Or, well, it's not synced. It's synced once and then marked read only. Wait, the write is performed on read-only page is copied. Okay, so it is synced. As the memory is no longer identical, yeah. Therefore, if only read operations are performed, the pages will not be copied at all. Why couldn't you just use the same address space? Maybe there's a good reason. I mean, there's probably a very good reason for that. Security, maybe, I don't know. Okay, but that's the heap, though. The copy will, well, exec is called immediately after fork. The copy will not occur. Right, because so exec is like making the thread be overtaken by some other process, well, executable basically. So it's like you call exec, your thread will be, you're executing a separate program which takes over, and then I guess you want to start at a clean slate for that, so the copy will not occur. Okay. However, there are a few points on the other side. Copy must happen in case for store reference. So when does the copy actually occur? Okay, I don't know. Am I going to think that in the case where the child never writes, it does not need its own stack to be allocated as both parent stack pointer, a child will simply move backwards through the stack. Hence, two pointers will separately move through a single stack, which will not change. Wait, so let me go through this. Am I correct thinking that in case the child never writes, it does not need its own stack to be allocated as both the parent stack pointer and child simply move backwards through the stack. Hence, two pointers will separately move through a single stack which will not change. But they have their own stack, right? The child does not have the same stack as the parent. They have their own stack space and own stack pointer. Like the stack pointer is a register, the thread will have its own version of that stack pointer. It's not sharing. One more thing, does the code region of the, unless I'm totally misunderstanding that, does the code region of the parent's virtual address space ever need to be copied? Since the data in this region is effectively read only this you need a few miracles to line up. For instance, you need ensure will stack. It's like I'm getting these random tidbits of knowledge that might puzzle into something that I can use. I don't know. When a process forks, any shared mappings that includes executed mappings remain shared. Something almost certainly will be written to the stack as most of the registers are found. Having call save registers during system calls will prevent data from being written to the user space stack. So why are you saying that this feature makes it more likely that they were written to the user space stack? For this reason, I would expect that XAB, like any other system call, would only affect the kernel stack, not the user stack. The kernel stack? You're right, registers generally say to a kernel stack on x86 because the nature of TSS means to you very much. Switch stacks every time, change power privilege ring. I think they're meant if you invoke exec using libc rather than using raw int x80. The call instruction itself will push a return pointer onto the stack. I don't know what is the kernel stack. I don't really know about that. I mean, I guess it would be. I mean, because user space stack. It's like, yeah, because as I understand it, each thread has its own stack. Keep repeating that. Okay. I don't know if it's why is this way because of language but it seems a lot of wasted effort that spawns a copy of the process that calls it. Perhaps it's useful sometimes, but majority of the times. Alright, so people are angry because it just does a bunch of copies. And it's maybe slow. I don't know. One big advantage of having parent duplicated as a child is that it allows the parent to program to make customizations to the child's program's environment before executing it. For example, the parent might want to read the child process standard out, in which case it needs to set up the pipes in order to allow it to read that before executing the new program. And that's exactly what we're doing as well with our virtual threads. It's also not as bad as it sounds efficiency-wise. The whole thing is implemented in Linux using copy-on-write semantics for the process memory, except in special cases known in the man page. But that's okay. vfork. Okay, I think let's just think about this a little bit. As I understand it, fork doesn't care about stack. It just copied the entire program memory, but the copy is virtual until actual write happens. So a section of memory is copied as soon as it's modified. Right, but this isn't even talking about writing. This is talking about reading. Because, sure, each thread has its own stack. Okay, maybe I've done this in a bad way, because the way I've done the virtual machine is that, let's say, okay, let's do like a new one here, virtual machine. So let's say we have a thread, so main thread has okay, let's do this program. The way this works is that a program, this is the whole program with all the threads, has shared things. Now, what is in the shared things? And what does shared mean? Shared means that all threads can access the shared things. Okay? So we have read-only data or memory. So that is a place where you can put read-only memory. Well, that's where we put like literal strings and stuff like that. Literal strings, etc. And like time known stuff. And then we have the heap is also shared, because it's like, I mean, the way that I mean shared is basically what. Okay, we can go through what that means, and then we also have like the instructions. Okay, and then we have the threads. Let's not worry about. Let's just have a one thread. What does a thread has private things? So the thread has the stack, which is private, and it also has the registers, which is private. So basically, a thread cannot access the registers of another thread, basically. So that's, I'm just explaining how my virtual machine works right now, because I realize that there might be some issue here. Okay, and then I want to explain, okay, how do we actually know if we get, let's say a thread gets an address. So let's say we have this instruction here, set address, 0 to be 1, let's say. Okay, what is going on here? So what we're doing here is that first we're mapping this address, and that will yield a location. And what is a location? Well, a location is either going to be a read-only or read-only with an address, or it's gonna be a heap with an address, or the stack with an address. It can also technically be an instruction address, but or it could also be the a register with some kind of tag as well. So these are the different things that we're mapping this to, and the way we're mapping it is that it's based on the value here. 0 would likely map to the read-only memory, because the memory layout is like this. Memory layout. First we have the read-only memory, and that goes from 0. We basically have like something like this. That goes from 0. Wait, is this a 4-bit? 4-byte, I mean. Yeah, whatever. Let's just do 32-bit memory. So this goes from 0 to, and then whatever, how much memory, like read-only memory, we need. But let's say we go up to FF here. Okay, so that is that, and then we have the next thing, which goes from, well, it goes from this, I think, and then like this is dynamic, like this changes depending on the program, so it doesn't have to be FF here. It could be depending on how much read-only memory we need. But let's just, for this example here, and then the next thing is goes out all the way up to like where the stack starts, and the stack starts, I don't know, somewhere, let's say over here. So this is the heap. Okay, and now what's important here is that, well, let's do the stack as well. So it goes from this to the end. This is the stack. Okay, that's the memory layout. So first we have the read-only at the start, then we have the heap from the end of read-only memory to start of the stack. Well, I just realized this is wrong here. This should be like this should be like F, and then this is like E, because you add 1 is gonna, yeah. Okay, so this goes from the end of read-only to the start of stack, and then the stack goes from the start of stack, of course, to the end of the whole thing. So this is the memory layout. The problem is that these two are shared, but this is private. And basically how I did it is that these two are grabbed from the shared space, right? But if you have an address that goes to stack, it's kind of like a virtual address space, right? You can't actually access other threads stack. If you have an address that goes to the stack, it always goes to your private thread stack to get it. So it's like you can potentially have two things with the same pointer, like address, but it goes to different stacks. It goes to whatever thread you're in. That stack is what you're referring to. So maybe that's the problem. Maybe the problem is that we should be able to refer to other threads stacks in this domain here. Because as I said, let's say we have, let's say this goes to FFFF0000. That means the first item on the stack. Hang on, I'll answer that question, Kugma. So we'll set this to 1. What that means is that what you're gonna do is we're gonna map it to the stack. The first. So this will so map address of this will yield stack number 0. So, but the thing is with the stack number 0 is that it depends on the thread. So this instruction will not change like this is not an absolute address. This is kind of like a relative address depending on which thread you're in. That's the issue, I think. Well, or that could be an issue. Yeah. So maybe I need to change this so that the stacks get like allocated. Their addresses will get like. I mean, either we could introduce pages that would say, okay, an address is not only like a 64-bit number, it's gonna be like two numbers, like the page and or the thread and then the address. Maybe, I don't know. Or we could try to fit everything into here, like all the processes share the memory space, the address space, so that you can refer to other threads stacks. But then that means that we have to share the stack space. So basically we have to kind of, each thread will get its own stack space and it has to fit, it has to kind of be allocated here. And then the stack counter has to point to the correct place, yeah. Why do you need multi-threading in Bash-like language? Yeah, I've answered this a couple of times. And the reason is that, well, for one, we're gonna have in the future we're gonna have support for asynchronous, expressions. so that you would be able to, well, let's say we have a function. You don't even need to have a function, but let's say you have a function here, and it's like echo hello, sleep 2, something like this. Okay, if we just call this, it's gonna block the main thread, right? But we don't want to. If you don't want to do that, you can do this. This would not block the main thread now, but it will still wait for 2 seconds and then echo. Yeah, so the multi-threading here is not actual threads like OS threads. It's a virtual machine. It's virtual threads in a virtual machine. But yeah, I believe you. Maybe we don't even need virtual threads, but that's the way I chose to solve this issue. Maybe you could do it in another way, but basically what we have is execution context that you can suspend and then continue whenever you need. I think fiber is a. I think that's a Microsoft term. That's like a Windows thing. But these are not operating system threads or fibers or anything like that. These are virtual threads that are run in a virtual machine that is coded in Runic. Like Runic has all the facilities to run this in its own virtual threads. Yeah. Concurrency, yeah, so yeah, and like in I think also like in Node.js also only has like one actual like thread in. It runs on one thread, but it still has async because it has like these micro tasks, or it has like a task queue or whatever. But I'm not sure how they do it. But yeah, I guess it might be something similar here. Because the way I do it's basically I just have a list. I mean, I can show you. We have the context here. So this is like the whole program here. Here's the shared context. And here's the threads. And they're basically just a list of thread contexts. And the context includes things like the stack, the registers, and that's basically it, the stack and the registers. Pipe threads is not really used. So the program context here, this includes everything we need to keep track of how to run a program in Runic. So we have like thread ID counter, which takes up which thread ID we're gonna spawn next. We have the thread counter, which is used for which thread is currently executing. Pipes is like a list of or map of pipe handles to the pipes that are currently active. and then closables are kind of like a abstraction on things that can exit, i.e. processes. So we have like a list, so we have like a map of pipes, like handles to pipes. We have also handles to close, like process that closes, so that you can have a instruction called wait, which waits on either a pipe or a closable until it's closed, and then it continues execution. So yeah, so everything here is like the virtual machine to be able to this is the data part to be able to run the program, and then we also have the evaluator, which will evaluate each instruction. It's like the CPU basically. Go routines also use growable stacks, for example, as far as I know, so you don't allocate entire stack immediately. Yeah, the reason why I was thinking like we need to copy the stack is basically because of the fact that we're sharing the address, or we're not sharing the address space right now. Each thread gets their own stack, both in like, and it's totally separate. So the thread cannot actually refer to other threads stack, but we could change that so that the address space is shared. And the way it works here is if we go to the evaluator and then we go to the step function. So you would call step to step through the next instruction on the current thread. So we're getting the current thread that is supposed to execute. And you can have this akin to kind of the operating system deciding which thread is currently, or which process currently gets to run, or whatever, something like that. And then the instruction, yeah, we get the current instruction and we run the instruction. And we get a result, which is like, should we continue running this this thread? And yeah, that's what's happening in step. And then we basically we call step until the program is done, basically. And that was the whole thing. Like, we need to be able to suspend execution to be able to stream pipes at the same time as we're executing things. And with the async thing, like, we also need to kind of have several execution contexts at the same time that we are stepping through, basically. I'm working on a language that's gonna work like Bash, except with a different syntax, basically. So yeah, maybe that's the solution, actually. And right now we're working on kind of figuring out how to share, basically how to share variables from one thread. Like in here, this is like the outer main thread, into here, which is ran in a separate thread. So that is the issue we're trying to solve. Hello. Yeah, unfortunately, I think I have to actually quit now. Why would you set 0x001 be addressing the read-only memory? Yeah, that was just an example to show, like, you wouldn't be able to do that. And yeah. Okay. So just so you can understand here, also is like, this is my virtual machine, so I've coded it, so I can decide if the read-only memory could be written over. So that is one thing. But I'm not being aggressive or anything. I'm just clarifying that this is not how basically like an operating system would work or anything like that. I'm just explaining how my virtual machine is working, so we don't mix that up. Hello, Minxio. I have never coded, but I really want to. You do know how I should start, the best way to learn? Sure, I have a couple of suggestions. Like, well, one thing that you would ask yourself is what you would like to build. I know that is maybe if you're going in like I just want to learn programming. Usually, maybe you have an idea of, do you want to get into web development, like building websites, or do you want to build like programs, games? Do you want to build like program robots? Like there's a lot of different, different reasons for starting to program. But usually I would recommend starting with Python, because that is an easy language to get into. And just starting up, just installing Python and just creating a Python file, and just start to write stuff there, and you can be able to run it directly. And it's an easy language, I would say. I want to be able to make scripts and programs and cheats for games. Okay. Single player, right. Okay. Well, then it's probably gonna be a bit more low level. If you want, I mean, okay, scripts and programs are kind of different things, and then games, cheats for games, that is kind of touching on, like, I guess that would be like, I don't know, I've never really done that, but basically I would assume you would go into like the assembly code and try to figure out how to do stuff there. I mean, there's probably a lot, like you're basically talking about making like cracks, or not cracks, but well, kind of the same idea, except you're trying to cheat instead of getting past some kind of thing there. I don't know. But yeah, so I mean, I think if you just want to learn programming, it's going to be a long journey, I would say. But okay. Okay, if you want to make scripts and programs, I would recommend Python still. Like cheats for games, I'm not that sure what you're gonna do there. But start with scripts. Start with Python for scripts and programs, because that is both, like, you can make scripts and programs. I mean, that's gonna be the same thing basically. Why should you be able to refer to other thread stacks? Okay, so the issue here is that this X here is kind of like a pointer to a string here, and it's stored on the stack. To be able to talk about X down here, like let's say we wanna, we just wanna echo X out, right? The issue is like, how in the or the intermediate representation language do we refer to X down here? That is the issue. Normally we would use the stack to be able to refer to X, and I can show you also. Okay, maybe it's easier if I show you how it works in C here. I have a compiler explorer up here. Okay, it's a little bit busy here, but basically in C, of course, you have these local variables, right? So you have I. You can see that I is stored on the stack here. So it's stored at RBP minus 12. That's the stack. And and then over here we have I plus equals X. Now I, how do we talk about I? We're using this to talk about I. 12 is the kind of compile time known address that we can use to talk about X. That's kind of like the, you could, it has to be like a unique address for this. But RBP is the stack frame. So that is runtime known. We don't know in compile time what RBP is, but we know that relative to RBP, 12 is always going to point to I. So that way we can talk about I as something, you know, tangible, that we can actually refer to as being the same thing in the same stack frame. If we would change the stack frame, we would lose that context. But we always have the stack frame in this function. This function defines the stack frame up here. So now, with that in mind, X, let's say X is on the stack. We refer to X down here, so we have to refer to the stack frame plus something. Now we already have like S over here, so maybe it's like stack frame plus 1, let's say. Okay. The problem though is that this thing is actually being run in a separate thread because of how the internal thing works here with piping out to things and spawning things. But that's not the issue. The issue is that we would like to have X be available inside here, even though it's a separate thread. So the problem is like, how do we wire this up? And well, it's kind of like so how this works is that internally this is creating another thread. We're executing, we're spinning up, we're connecting kind of the standard out pipe of echo to the standard out of the main process, and then we have a thread which kind of pulls data from the standard out of echo and writes it into standard out of the main process. Well, I say thread because when I say thread, I don't mean like an operating system thread. I mean a virtual thread in Runic, like a Runic thread. Let's call it a Runic thread. Okay, it's a virtual thread in the Runic virtual machine. The only reason I call it thread is basically because it has its own context, in the sense of it has its own registers and its own, like, well, stack space. Because it needs its own stack space, because it can mess with the stack, and it doesn't. You don't want the thread to mess with. Well, actually, no. Yeah, you don't want you don't want another thread messing with your stack, because then your stack counter will be like it won't be in sync with your instructions. So I think we need to have a separate stack. So that's why I'm calling it thread. To me, that means basically that it has its own registers and its own stack space. So it's separate from the other threads. The interpretation of the JavaScript in Node.js does happen in a single thread, so you can't have two pieces of JavaScript code running at the same time, but Node will create new threads for some. Like calling fetches something would could open a thread, but JavaScript would never know about it. Yeah. You're working with like the promises and stuff. Sure. But in my language, in Runic, we don't actually spawn any threads. Like, we don't spawn threads. Well, the only time we're spawning threads is when we're calling other processes. So when we're calling echo here, we're using the Zig standard library for spawning a child process, which does fork. But yeah. But we're strictly talking about the virtual machine now. We're not talking about like OS threads or anything like that. That's not the issue here. The issue is the virtual machine that I've built. And I'm trying to figure out how this X can get into here. And one idea was to change the stack addresses so that they are kind of like absolute address and not like relative address. Because then the threads could access their other stacks, but it also has to be like a lifecycle problem to be solved there as well. Because if the parent is like popping X off, then the child now doesn't have like access to that anymore. Or at least it's like volatile. And yeah, so maybe we actually do need to copy. And the same problem will arise when we're talking about, I mean, this is basically kind of like a closure. We're trying to make a closure here for X that the thread will be able to access. And one idea here was to put the kind of like a closure on the heap and then have the thread know about it through either like an extra stack in the thread, or not extra stack, but extra stack value. So we're kind of saying that, okay, well, relative to the closure pointer, X is here. So X is at the first, like, you know, we're allocating the closure here. We're setting the first element to X, and then we're giving the closure pointer to the thread, the Runic thread, and then the Runic thread would access X by saying, okay, well, it's gonna grab its closure pointer plus whatever element X is stored in. Something like that. But I'm kind of jumping between solutions here a little bit, trying to figure out, because I don't want an overly complicated solution. I want to have more. If we can find a more simple solution, that would be better. But it feels like a pretty hard problem, or at least you have to think about it a lot. But yeah, I really have to go now here, unfortunately. But yeah, this requires a little bit of thinking. So we didn't really get to do much this time, but did some research and had some good discussions. Thank you very much for chatting with me. Oh, you were watching 20 minutes behind live, right? That was interesting. You kind of is. I was like discussing things with you, and I wasn't sure if you actually saw or heard what I was saying. Yeah. Anyway, I need to actually go now. So, but yeah, we'll have to continue this and try to figure out a way to solve this here. But yeah, that's gonna be it for this time. So thank you very much for discussing this with me and joining me here. And hope you have a nice day. I have to go now, so bye bye.